In question number 2 of exercise 17b, it is given that a straight line is drawn cutting two equal circles. Equal circles means their radii are same, and passing through the midpoint M of this line joining the centers O dash. You have to prove that the chords AB and CD, which are intercepted by the two circles, are equal. So before starting the proof, we will try to utilize this theorem that if there are two chords in a circle, they are equal if they are equidistant from the center. Now, even if there are two different circles given here with different centers, but since the radius is the same, we can still apply the theorem imagining as if the two chords are part of the same circle. So if we have AB over here and CD over here, these two chords will be equal if they are equidistant from their centers. So if I draw a perpendicular line from the first circle with center O to AB, and let's say that this point is P, and we'll draw a perpendicular line from the center of the second circle O dash to the chord CD, and let's say that this point is Q. Then we just need to prove that OP is equal to O dash Q. So to do that, let us look at these two triangles, triangle OPM and triangle O dash QC, and let us see whether we are able to prove that they are congruent. If they are congruent, then we can easily say that OP will be equal to O dash Q. Alright, so let us see what sides or what angles are equal. I can see that angle OMP, this angle will be equal to angle O dash MQ because they are vertically opposite angles. Then angle OPM is 90 degrees and angle O dash QM is 90 degrees according to our construction. And what else is equal? Can I say that OM is equal to O dash M, because M is the midpoint of the line joining the centers O and O dash. So let us look at what are the equal things which we have. We have two angles which are equal, right? Two angles and one side. So can I say that using angle side congruency, triangle OPM is congruent to triangle O dash QM. This should be O dash QM, right? Okay, so if I have proved now using angle side congruency, now I can imply from this that OP will be equal to O dash Q because of CPCT. And now since OP is equal to O dash Q, I can say that the chords AB and CD are equidistant from the center, hence they are equal. Hence AB is equal to CD, hence proved. You just need to write the reason for each statement in brief. In question number 4, there are two circles given, one with center O and one with center O dash, and they intersect at points P and Q. It is given that there are two straight lines APB and CQD which are parallel to OO dash. Now you need to prove that OO dash is half of AB and AB is equal to CD. Two things. So to start this proof, before starting it, we need to do a construction. We need to drop perpendiculars from the centers to the chords of the circles. So from center O, I'm dropping perpendiculars OM and OX to the chords AP and CQ, and from center O dash I am dropping perpendiculars to chords PB and QD meeting at N and Y. So this is my construction. After this I can start the proof. So first step I can look at is trying to prove that O M N O dash, that quadrilateral, is either a parallelogram or a rectangle. I just need to prove that the opposite sides OO dash and MN are equal. So I can do that by proving either of these. So it is given that MN is parallel to OO dash, and by our construction OM is perpendicular to AB and O dash N is perpendicular to PB. So we have two 90 degrees over there, which sort of says that the sides OM and O dash N have to be parallel to each other, because these are two lines which are perpendicular to the same straight line. Otherwise, you can also prove that all the four angles have to be 90 degree. You can use properties of parallel lines and transversals, right? There are three given parallel lines, and you can identify the transversals to say that all the four angles within this quadrilateral are 90 degree. Hence, you are proving that it is either a parallelogram or a rectangle. To be specific, it is a rectangle. But we just needed to prove the fact that OO dash has to be equal to MN. Opposite sides are equal. Okay, so now after we have proved this, we have to prove another part. So looking at the smaller circle, OM is perpendicular to the chord AP. So I can say that the part MP is actually half of the larger chord AP, because the line perpendicular from the center to a chord will bisect the chord, right? So that is why the smaller portion MP of the chord AP is actually half of it. Similarly, for the other circle with center O dash N is perpendicular to the chord PB. Therefore, I can say that PN, this smaller part, PN has to be half of PB for the same reason. Now, if I add MP plus PN, I have half of AP plus PB. Now, MP plus PN gives me MN, and that is actually equal to half of AP plus PB. Now AP plus PB is half of AB, right, from the figure. Now if MN is half of AB, and I already know that OO dash is equal to MN, so I can substitute MN as OO dash. So OO dash is half of AB. This is the first part of my proof. Similarly, I can try to prove that CD, so OO dash should be half of CD. I can prove this by taking the quadrilateral OO dash, or let me say OXY dash. If I look at this triangle, if even this is, let's say, a parallelogram or a rectangle, we can use the same properties of lines and angles to prove that that is a parallelogram or a rectangle. So hence I am proving that OO dash will be equal to XY. And then again I will use the same property of circles to say that since OX is perpendicular to the chord CQ, I can say that XQ is half of CQ. Since this perpendicular line OX will bisect the chord CQ, so the smaller portion XQ is actually half of the larger chord CQ. Similarly, for the other circle, with center O dash, since O dash Y is perpendicular to QD, therefore this smaller part QY will be half of the chord QD. So QY is actually half of QD. Now again I can add these two portions, XQ plus QY. XQ plus QY will be equal to half of CQ plus QD, which means XY is actually half of CQ plus QD gives me CD. So if XY is half of CD and I knew that OO dash is equal to XY, therefore I can connect the two equations to say that OO dash is actually equal to half of CD. Now from here, this equation OO dash is half of CD and OO dash is half of AB. The left hand side are equal, so I can say that half of AB is equal to half of CD. The right hand sides must be equal, which implies that AB equal to CD. This is the second part of the proof which I wanted. In question number 6, we have a circle with center O and there is a square OABC which is drawn. Now we have to prove that triangle OPA is congruent to triangle OQC. You can join the two sides AP and CQ. Then let us look at in these two triangles which sides or which angles are equal. So first we can observe that angle POA from the first triangle is actually equal to angle COQ from the second triangle because it's the common angle. Both are actually 90 degree. So you can write that angle POA is equal to angle AO angle QOC. These two are the common angle. Then what else do we have? We have from the first triangle OPA, the side OA is equal to side OC from the second triangle, right? Because these are sides of the same square, so OA is equal to OC. Then what else do we have? We have from the first triangle OPA, we have OP, which is one of the radius. This is equal to OQ. They are the radii of the same circle, so OP is equal to OQ, and OP and OQ are sides of these two triangles. So we can see that there are two sides which are equal and the angle in between these two corresponding sides are equal. So we have a side angle and a side which are equal, right? So if I'll just focus on triangle OPA, this side OP, this angle, and this side OA, these are the three corresponding sides and angles which are equal to the other triangle. So using SAS congruency, I can say that triangle OPA is congruent to triangle OQC. In the second part of the question, we have to prove that triangle BPC is congruent to triangle BQA. So you can join the sides BP and BQ and then see which sides and which angles are equal. I can see that in BPC, angle BCP is equal to angle BAQ because these are angles in a square, they are 90 degrees, so they are equal. And right, angle BCP is equal to angle BAQ. Then I have BC is equal to BA because these are sides of a square, so B is equal to BA. And then for the third congruent part, what I can look at is, I know that OC is equal to OA. These are sides of the same square. Now I have OP and OQ, which are radii of the same circle, and even those are equal. So from OC I can subtract OP, and from OA I can subtract OQ. OP and OQ are the same quantity. I'm allowed to subtract the same number from both sides of the equation. Now after subtracting, what is remaining is, if I do OC minus OP, I have this side CP which is remaining, and if I do OA minus OQ, I have the side AQ which is remaining. So I can go ahead and say that CP is equal to QA. So in these two triangles, if I look now, I have a side angle and a side which are equal. So from SAS congruency condition, I can say that triangle BPC is congruent to triangle BQA. Let us look at some properties related to arcs and chords and the angles subtended by them in a circle. We can have a chord like this AB in a circle, and then if we have this point P over here, this curved region APB, this portion of the circumference, is the arc cut by the chord. This is the minor arc. Now let's say that we have another chord CD with the same length as chord AB, and let's say this is point Q. Then the arc which is formed by the chord CQD, this portion of the circumference, and if I know that if the arc APB is equal to the arc CQD, if these lengths are equal, that means that even the chords AB and CD are equal. Even the opposite is true. If I knew that the chords AB and CD are equal, then that also means that the corresponding arcs APB arc will be equal to the arc CQD. So this is one property related to arcs and chords. Then the next property is related to the angle subtended by the arcs or the chords. So let's say the chord AB is subtending this angle AOB at the center, and the chord CD is subtending angle COD at the center. If I know that angle AOB is equal to angle COD, then I can also imply that the chords AB and CD are equal, which also eventually means that the arcs APB and the arc CQD are also equal. And even the converse is true. If suppose I knew that the chord AB is equal to chord CD, which also means that the arc APB is equal to the arc CQD, then such equal chords or such equal arcs subtend equal angle at the center. So I can also imply that that would mean angle AOB is equal to angle COD. These are the theorems related to arcs and chords. These properties of arcs and chords can be easily proved using the concept of congruent triangles. Also, these properties are valid if we had two separate circles but with the same radius. So essentially, if we have two equal circles, then these properties are still valid. Now, an extension to these properties are that it's not just about being equal. The length of the arcs and chords and the angle subtended at the center are proportional. So for example, if I have in a circle, there's a chord AB of length let's say 6 centimeter, and it is subtending some angle at the center O, angle AOB, and there is another chord CD which is, let's say, of length 3 centimeter. Let's say it's of length 3 centimeter and it is subtending an angle COD at the center. Now there is a relation between the angle subtended. So if I look at the ratio of the lengths of chords AB and CD, it will be equal to the ratio of the angle subtended by these chords at the center. So since AB was twice of CD, this ratio of angles AOP and COD will also be equal to 2:1. So the angle subtended by AB will be double that of the angle subtended by CD. The length of the chords or the arcs with the angle subtended at the center are proportional. Then another property is that if we have a regular polygon means a polygon with all the sides which are equal, and if you inscribe a polygon inside a circle, for example, I can look at a triangle. I can have a triangle which may be inscribed in a circle. Rather, the circle is circumscribing the triangle. And if I know that this is an equilateral triangle, then I know that ABC, these chords are of equal length. Then they should subtend equal angles at the center. So if I join these sides and center is O, I can say that angle AOB is equal to angle AOC, and that is equal to angle BOC, because equal chords subtend equal angle at the center. Now if I add all these three angles, these are angles around this point O. These are the angles around the center O, and the sum of these three angles has to be 360 degrees. So, and also these three angles individually are equal to each other. Therefore, each angle has to be equal to 360 divided by 3, which here is 120 degrees. So angle subtended by an equilateral triangle is 120 degrees. So if suppose I know that this chord AC is the side of an equilateral triangle, then I know that the angle subtended by this chord AC has to be equal to 120 degree at the center. Similarly, I can take an example of any other regular polygon. So if I had taken a square which is a regular quadrilateral, all the four sides of the square are equal, and if this is being circumscribed by a circle and I have the center like this, then if I join these, then I have four angles which are being subtended at the center, AB, CD. So essentially AB, BC, CD and DA are four chords which are of equal length. So they also are subtending equal angles at the center of the circle. And again, this remains true that all the angles around the center point O, has to add up to 360 degree. So the only possibility is that each of these angles, AOB, BOC, COD and AOD, each of these angles have to be 360 degree divided by 4, which is 90 degrees. So if it was given that there is a chord AB of a circle, and this side AB is actually the side of a square which is a regular polygon, and this polygon has four sides, then I can automatically calculate the angle subtended by the chord AB at the center, and that will come up to be 360 degree divided by 4, the number of sides of the regular polygon, which is 90 degree. This is true for any regular polygon of any sides, be it 3 sides, 4 sides, 5, 6, 7, 8, any number of sides. In exercise 17C, question number 1, this is the given figure, and an equilateral triangle ABC is inscribed in a circle with center O. You have to find out two things. First, the angle BOC. So let us focus on that. Angle BOC. Now it is given that triangle ABC is equilateral. So we have came across the property that if a chord in a circle is the side of an equilateral triangle, so if I look at the side BC, since this is a side of an equilateral polygon, equilateral triangle, therefore the angle which this chord BC is subtending at the center, which is angle BOC, will be equal to 360 degrees divided by the number of sides in the regular polygon. So now an equilateral triangle has 3 sides, so 360 divided by 3, which is 120 degrees. So angle BOC is 120 degrees. Alright, now that we have found out angle BOC, we have to find out the second angle, which is angle OBC. OBC is over here. Now we can utilize the angle sum property in a triangle. So if I'm looking at triangle BOC, I already know angle BOC, and I can also identify that OB and OC are of equal lengths because these are radii of the same circle. Therefore this is an isosceles triangle, and hence angle OBC will be equal to angle OCB. These two are equal angles, right? So if I just denote by x and x, therefore in triangle BOC by angle sum property I can just say that 120 degree plus x is equal to 180 degree. Therefore I can say that 2x is equal to 180 minus 120, which is 60. So x is equal to 60 by 2, which is 30 degrees. So angle OBC is equal to 30 degree. This is answer to my second part. In question number 3, we have a circle given with center O, and it says that AB is a side of a regular pentagon and BC is a side of regular hexagon. And then we have to find out the measures of 6 different angles. So let us look at it one by one. Let us start with the first angle, which is angle AOB. Angle AOB is over here. So since AB is the side of a regular pentagon, we know that it has 5 sides. Okay, and we know the property of chord. So since AB is a chord of the circle and AB is also a side of a regular pentagon, therefore the angle which AB subtends at the center can be found out by taking 360 degrees divided by 5, because the pentagon has 5 sides. So I can divide 360 by 5, and if I calculate that, I should get 72 degrees, right? Yeah. So measure of angle AOB comes up to be 72 degrees. Alright, then we have to find out the measure of angle BOC, which is over here. Now I know that BC is a chord, but BC is also a side of a regular hexagon. Now a hexagon has 6 sides, so I know that the angle subtended by BC at the center will be equal to 360 degree divided by 6, the number of sides in a hexagon. So this comes up to be 60 degrees. So angle BOC is equal to 60 degrees. Then the third is find angle AOC. Now we know, looking at the figure, angle AOC is actually the sum of angle AOB and angle BOC. So if you add 72 and 60, you will get 132 degrees. That is angle AOC. Then we have to look at the next angle, which is angle OBA. OBA is over here. OBA is over here. Now again we can use two things, angle sum property and property of an isosceles triangle. So if I look at triangle AOB, I know that OA and OB are equal sides because they are radii of the same circle. Therefore, the angles opposite to it, so angle OBA and angle OAB, have to be equal. So if I assume they are x and x by using angle sum property in triangle AOB, and I know that angle AOB is 72 degrees, so I can say that 72 degree plus x is equal to 180. So twice x is equal to 180 minus 72, which comes up to be 108. So x is 54 degree. Therefore angle OBA is 54 degrees. Then the next angle is angle OBC. Where is angle OBC? It is over here. So again, similar to how we found the previous angle, if I focus on triangle BOC now, and I know that angle BOC is equal to 60 degree over here, and if I assume that angle OBC is y, angle OCB is also y. The reason is OB and OC again are radii of the same circle, so it's an isosceles triangle. Angles opposite to the equal sides are equal. So again I can make an equation saying that in triangle BOC, 60 degree plus y is equal to 180 degree, angle sum property of a triangle. So 2y is equal to 180 minus 60, which is 120. So y is 120 by 2, 60 degree, which means angle OBC is equal to 60 degrees. And the last one is angle ABC. If I look at angle ABC, it is actually this angle over here, this complete one. Angle ABC is actually sum of angle AOB plus angle OBC, this entire angle. If I take the sum of these two, so angle AOB I found out as, sorry, ABO is that x degrees, so it is 54, right? I am trying to do angle ABO plus angle OBC. So ABO according to our calculations was 54 degrees, and angle OBC we found out as 60 degrees. So 54 plus 60 is 114 degrees. So angle ABC is 114 degrees. In question number 5, it's given that in the figure the lengths of arcs AB and BC are in the ratio 3:2. And if angle AOB is 96 degrees, we have to find two angles. First, let us focus on finding angle BOC. BOC is over here. Okay, so now it is given that the ratio of length of arc AB and BC is in the ratio 3:2. 3:2. So we know one property of arcs and chords, that if there are two arcs or chords in a given ratio, they subtend an angle at the center in that same ratio, right? So if it is given that the ratio of arc AB or chord AB, you can also imagine, divided by the ratio, the length of arc BC or chord BC, this ratio should be equal to the angle subtended by these arcs or these chords, right? So angle AOB is to angle BOC. So this ratio has to be 3:2. So this fraction I can write as 3/2. And since angle AOB is given as 96 degree, so 96 degree divided by angle BOC is 3/2. I can take reciprocal on both sides. So angle BOC divided by 96 is actually 2 by 3. Hence angle BOC is equal to 2 by 3 into 96. And if I simplify this, twice of 32, angle BOC is equal to 64 degrees. So this comes up to be 64. Alright. Then the second part is finding out what is angle ABC. ABC is over here. Now before finding ABC, let me just split this into two angles. Let me split this into angle ABO and angle OBC. I am splitting this, so let's take this as X and this is Y. Now again I can use properties of isosceles triangles, and since AO, OB and OC are radii of the same circle, these are of equal lengths. So in triangle AOB, these are the equal sides AO and OB, so therefore the angles opposite to them have to also be equal. And similarly for triangle OBC, that other angle has to be Y. So looking at triangle AOB, I can use angle sum property now. So 96 degree plus X is 180. So twice of X is 180 minus 96. I will get 84. So X is half of 84, which is 42 degree. And for triangle BOC, I have 64 plus Y is 180, angle sum property. 2Y is 180 minus 64, so 120, 116, let's say. Yeah, so Y should be equal to 50 and 8, 58 degree. Therefore angle, I have to find angle ABC, which is actually X plus 5, 42 plus 58 degree, and this comes out to be 100 degrees. Therefore angle ABC is 100 degrees. In question number 7, in the given figure, AB is the side of a regular hexagon and AC is the side of a regular 8-sided polygon, which is an octagon, but the necessary information is that it has 8 sides. Now you have to find out the measures of 4 different angles starting from angle AOB. So let's focus on AOB, which is over here. So AOB is the angle being subtended by the chord AB at the center, and it is given that AB is the side of a regular hexagon, right, which has 6 sides. Therefore angle AOB, the angle subtended by the chord AB at the center, will be equal to 360 degree divided by 6. 6 is the number of sides in a hexagon, so this is equal to 60 degrees. So angle AOB is 60 degree. Then the next angle is angle AOC. Now AOC is the angle being subtended by chord AC, and chord AC is actually a side of a regular 8-sided polygon. Therefore the angle subtended by chord AC, which is angle AOC, is equal to 360 degree divided by 8, because it is part of a 8-sided polygon, regular polygon. So if I divide 360 divided by 8, I should get 180 by 4, 90 by 2, 45 degree, right? So that is why angle AOC is 45 degree. Okay. Then the next part is to find angle BOC. Now it is easy to see from the figure, angle BOC is actually the sum of angle AOB plus angle AOC. So I can simply add 60 plus 45 to get 105 degrees. That is angle BOC. And the last part is to find angle OBC. OBC is over here. Now I can look at triangle BOC, and because I already know angle BOC is 105, and I also know that OB and OC are radii of the same circle, therefore a triangle OBC or BOC is an isosceles triangle. So if this is x degree, then the other angle is also x, opposite sides of the equal sides of an isosceles triangle, right? Then I can again use angle sum property in triangle BOC to say that angle BOC, which was 105 degrees, so 105 plus x is 180 degrees. So twice of x is 180 minus 105, so that is 75 degrees. So x will be equal to half of 75 degrees, which is 37.5 degrees. 37.5 degrees. Therefore, angle OBC is 37.5 degrees.